what we will be discussing today is the concept of cascaded amplifiers. And cascaded amplifiers simply means applying the output of one amplifier circuit to serve as the input of a second amplifier circuit. So for example, let's say that we have the following circuit. There are lots of random noises happening. So we have this circuit, and let's say for the sake of argument that this is a 10 kilo ohm resistor and this is a 5 kilo ohm resistor. And here we have a 1 volt signal. And we take this output signal and we apply it to the input of a secondary amplifier stage, like so. Call this the V out for the whole thing. And let's say that this is a 4 kilo ohm resistor and an 8 kilo ohm resistor. And let's ground this terminal here. Okay. So there are two ways that we can analyze these circuits. And the first way that I'm going to talk about is definitely the hard way. And it is effectively what we should do if we don't recognize what it is that we are looking at, okay? So what I'm going to do is I'm going to label my nodes here, okay? So I'm going to call this node A. I'm going to call this node B. I'm going to call this node C. And I'm going to call this node D. And we are effectively just going to apply Kirchhoff's voltage law at these nodes, Kirchhoff's current law at these nodes, but we are going to run into some very specific problems that I'd like to talk about in this application here, and we'll talk about how they get resolved, okay? So if we look at KCL at node A, where, to be clear here, both of these amplifiers, let's call it A1 and A2, employ negative feedback. So we are going to use our ideal op-amp rules, okay? So if we apply KCL at node A under the constraint that no current can flow into or out of that input terminal, what we see is that we will have VA, over 5 kilo ohms plus VA minus VB over 10 kilo ohms is equal to 0. Nothing wild or crazy there. If we apply KCL at node B, we're going to run into a difficulty. And so let me explain what I mean by that explicitly. The current that's flowing up through the 10 kilo ohm resistor is easily defined in terms of our nodal voltages. That would simply be VB minus VA over 10 kilo ohms. And the current flowing to the right through our 8 kilo ohm resistor would be VB minus VC over 8 kilo ohms. The problem that we have is that there may be some current here. I'm going to call it I out 1. It's flowing into or out of the output terminal of the op amp. And that current has no relationship whatsoever to any of the quantities listed in this circuit. Okay. So if we were to apply KCL fully, we would have to add that current I out 1 here and set this guy equal to 0. But there is literally no way for us to determine what that current I out 1 is without physically measuring it. Okay. What that means is that we cannot rely on this KCL at node B equation because it contains an undefinable unknown quantity. Okay. So we have to throw that relationship away. If we apply KCL at node C, what we will find is that we have VC minus VB over 8 kilo ohms plus VC minus VD over 4 kilo ohms is equal to 0. And then when we try to apply KCL at node D, we wind up running into the exact same problem as we saw previously, right? We'll have VD minus VC over 4 kilo ohms plus this current I out 2, whatever it happens to be, is equal to 0. And again, we have no means by which to quantify I out 2 in terms of our nodal voltages or anything else. So we have, let's see, VD minus VC over 4 kilo ohms plus I out 2 is equal to 0, which again, we cannot use. So the expectation here is that we should have 4 equations and 4 unknowns. We can't use any of our KCL equations at the output of an ideal op amp. So where are our other 2 equations going to come from, Bradley?
Voltage relationships from the ideal op amp.
Exactly correct. So our other equation comes from the fact that VA has to be exactly 1 volt and VC has to be exactly equal to 0 volts. If we solve this system, so this is equation 1, equation 2, equation 3, and equation 4. If we solve this system, we will find that V out is, I believe, my stylus will write here, -1 volt. Okay. By all means, solve it and check this. I'm getting this result by looking at this circuit from the perspective of the easy way, which is what we're going to talk about here in a moment. Okay. So if we have a cascade of amplifiers that we don't recognize, okay, or some configuration that we haven't seen before, we would have to employ this method where we systematically apply KCL at our inverting input nodes and use the voltage relationships from our ideal op-amp rules to figure out how our input signal propagates from here to the output of the combination, okay? That's the hard way. Not particularly difficult. The only potential pitfall is that we have to recognize we cannot apply KCL at our output nodes of any of our ideal op-amps. Okay?
Check -3 or -1.5.
You're right here because I made a mistake there by saying that that stage was a inverting because it's not. So that should have a gain of 3 and that should have a gain of -1/2. So it should be -1.5 volts. Yep, that's my mistake. Thank you, Bradley. 10/5 is 2, 1 + 2 is 3. So this should be 3 volts here times a factor of -1/2 should be -1.5. Yeah. All right. So I've kind of already walked you through the second practice here. So what I'm going to do, I'm just going to make a quick copy of this and talk you through the easier way to treat a cascade of op-amp circuits. So what I'm going to do here is I'm simply going to divide my circuit into 2 discrete stages. Everything to the left, I'm going to call stage 1. Everything to the right, I'm going to call stage 2. The output of stage 1, Vout1, serves as the input signal Vn2 of stage 2. So if we ignore everything to the right of the dashed red line here, what does stage 1 look like? Exactly right, a non-inverting amplifier. So stage 1 is a non-inverting amplifier, which, if you recall from Monday's lecture, has a voltage gain, which I'm going to call it AV1 of 1 plus R2 over R1. For this particular circuit, then, that looks like 1 plus 10 kiloohms over 5 kiloohms is equal to 3 volts per volt. And from that, the quantity Vout1 is 1 volt times 3 volts per volt is 3 volts. Right? How everything to the left of the dashed red line behaves, we have covered before. Now, ignoring everything to the left of the dashed red line, what does the right side look like? I disagree.
Well, I mean, not in terms of the,
It's an inverting amplifier because the input is being applied on the inverting side, right? If it were a non-inverting amplifier, this input would need to be changed over here, okay? So stage 2 is an inverting amplifier. Where the voltage gain of our second stage, AV2, is negative R2 over R1, which in this case is negative 4 kiloohms over 8 kiloohms, or negative 1/2 volts per volt. And so V out 2 is V in2, which was 3 volts, times our voltage gain of negative 1/2 volt per volt is negative 1.5 volts. Another way to think about this is that we have our input signal of 1 volt being multiplied by the voltage gain of amplifier 1, and then being multiplied by the voltage gain of amplifier 2 to give us our output voltage, where the product of AV1 and AV2 is just A, the total gain of our system.